So dear students, let us see this note. For a lossless transmission line, impedance of transmission line at d distance from load is Z0 ZL plus JZ0 tan beta d divided by Z0 plus JZL tan beta d. Okay. Now first one, case 1, lambda by 8 transmission line. Let us take lambda by 8 transmission line and let us see the input impedance of that. So total length of the line is lambda by 8. Okay. Total length of the line is lambda by 8. Now the load impedance is ZL. Characteristic impedance of the transmission line is Z0. Now D0 means what at load? D is equal to total length. D is equal to total length means you came to input side. Now what is the input impedance of lambda by 8 transmission line? So beta into D is equal to 2 pi by lambda into lambda by 8. So that is lambda cancel, you get pi by 4. Now if you substitute Z is equal to total length here, total length is lambda by 8 actually, then you get input impedance. So Z0 ZL plus JZ0 and tan pi by 2 divided by Z0 plus JZL tan pi by 2. Now total length is lambda by 8. You are substituting D is equal to lambda by 8. That means it gives input impedance. So input impedance of lambda by 8 transmission line is Z0 ZL plus JZ0 divided by Z0 plus JZL. So this is the formula, you have to remember this one. So in examination, anywhere if you see lambda by 8 transmission line, if you want input impedance, then this is the formula. Again and again you should not solve there. So Z0 ZL plus JZ0 divided by Z0 plus JZL. Now I will tell you one simple statement here. For lossless transmission line, Z0 is equal to root L by C is equal to R0, it is real. For lossless line, if load is real, that means ZL is equal to RL. Okay, if load is real, then Zin of lambda by 8 is equal to this one is R0 plus 1 minute. So this is R0 and here ZL is RL plus J R0 divided by Z0 is R0 plus J RL. Okay. Now this is RL plus J R0. Here RL is different value, R0 is different value, so you can't cancel them. So anyway, now if you take modulus of this one, then you get R0. This is root of RL square plus R0 square divided by root of R0 square plus RL square. Ultimately this cancel. So you get magnitude of input impedance of lambda by 8 line is R0. So what is the statement here I was telling you? For a lossless lambda by 8 transmission line, if load is real, then magnitude of input impedance is equal to characteristic impedance, and also this impedance input impedance is complex, but magnitude is equal to R0. I will write the statement here. For a lossless lambda by 8 transmission line having a real load, the input impedance is complex. Here no complex, no, it is this one. Complex by complex is complex. Complex having a magnitude as characteristic impedance, that is R0. Okay. Now let us take case 2, that is lambda by 4 length transmission line. 1 by 4 means quarter, lambda means wavelength. So lambda by 4 is called quarter wavelength transmission line QWT. QW means quarter wave, T means transmission line. So quarter wave length long transmission line, that is briefly. Okay. Quarter wavelength transmission line. Simply short name is, it is called as QWT. Okay. Now total length is given as lambda by 4. It is given total length of the transmission line. This is load. This is characteristic impedance, and D is equal to 0 at load. Now D is equal to lambda by 4, and ultimately here Zin of lambda by 4 it is. If you substitute D is equal to total length, then you come to input, the input impedance of lambda by 4 transmission line, Zin of lambda by 4. Now let us substitute beta into D. So beta is 2 pi by lambda multiplied with D. D is actually lambda by 4, and lambda cancel. So pi by 2. Now here if you take D is equal to lambda by 4, I will do one thing. This is Z0, then ZL divided by tan beta D plus JZ0 divided by, here Z0 divided by tan beta D plus JZL. Okay. So actually Z0 ZL plus JZ0 tan beta D divided by Z0 plus JZL tan beta D, because we brought this tan beta D, we pulled out tan beta D, so that here tan beta D cancel, because it is becoming tan pi by 2 infinity. So we have to use L hospital rule. Now Z at D is equal to lambda by 4 is equal to Z0 ZL divided by tan pi by 2 is infinity plus JZ0 divided by Z0 divided by infinity plus JZL. Now this is named as input impedance. It is named as input impedance of lambda by 4 transmission line, that is Z0. So JZ0 divided by JZL. So here JJ cancel, Z0 square by ZL you get. So this is the Zin of lambda by 4. In examination you get this many times, student. So what is the input impedance of lambda by 4 transmission line? Characteristic impedance of the transmission line square divided by load impedance of this transmission line. This is very important. this one. One more conclusion is from this, the input impedance of lambda by 4 transmission line and the load impedance of lambda by 4 transmission line is equal to characteristic impedance of that line whole square. So this is also important. This equation is used in impedance matching of quarter wave transformer. Actually, I will tell you this in different way. First of all, you observe this one. What is Z in of what is this? This is the lambda by 4 length transmission line. What is the input impedance? That input impedance is named as Z in of lambda by 4. This one. What is the load impedance to this one? ZL. Once again, I am telling, at the starting of the lambda by 4, what is the impedance? Z in of lambda by 4. At the ending of the lambda by 4, what is the impedance? ZL. Multiply them. So impedance into impedance is equal to impedance square. So here that impedance is characteristic impedance of this transmission line. This is a very important observation. You can see here, I am writing, there is a one transmission line whose length is lambda by 4 actually. Okay. Now let us say this is characteristic impedance Z0. Otherwise sometimes they take ZQ. Q means quarter wave transformer. Characteristic impedance. ZQ means quarter wave transformer characteristic impedance. So here let us take Z2 is present here impedance. Let us take here Z1 is present impedance. So now what I am telling is for lambda by 4 length transmission line, at the input impedance is Z1 and at the output, that means after completing lambda by 4 length impedance is Z2, then that is equal to characteristic impedance whole square. Okay, and here Z1 is input impedance of lambda by 4 transmission line. Z2 is load impedance of lambda by 4 transmission line, and ZQ is characteristic impedance of lambda by 4 transmission line. Okay. Now case 3, this is also very important. We are going to get very important observation. Smith chart is drawn for lambda by 2 length. The reason we will see here. So this is lambda by 2 transmission line, half wavelength long transmission line. This is a half wave length long transmission line. Now let us say the length of the transmission line L is equal to lambda by 2. Okay, and this is ZL, this is Z0. Okay, now D is equal to 0. D is equal to 0 means at load D is equal to lambda by 2, and this is Z in of lambda by 2. Okay, now beta into D is equal to 2 pi by lambda, and D is equal to lambda by 2. Now that is nothing but lambda cancel, 2 to cancel, you get pi. Now in that formula substitute D is equal to lambda by 2, that means Z0 ZL plus JZ0 tan beta D is pi divided by Z0 plus JZL and tan beta D, so that is tan pi. Ultimately this we are calling it as a input impedance of lambda by 2 length transmission line. So that is nothing but this 0, Z0 cancel, you get ZL. Utmost important conclusion, very important. This is what is the discussion here, students? Anyway, first I will complete this, then we will go to that. What is the input impedance of half wavelength transmission line? That is equal to load impedance of the transmission line. Here, for example, if load is short circuit, input also short circuit. If load is open circuit, input also open circuit. That is why this can be used to reject some frequencies also. To reject some frequencies. Okay, anyway, if you want, I will tell you that also. Now, at load here, that means at D is equal to 0, impedance is, we know that at load impedance is ZL, but we are substituting in this formula and we are finding that so at D is equal to 0, you get Z0 ZL plus JZ0 tan 0 divided by Z0 plus JZL tan 0. So, you substitute tan beta D D 0, then this is 0, this is 0, Z0 cancel, so you get ZL. Actually, already you know, student, at load impedance is ZL, you know, but I am telling you, you substitute D0 in this formula, then also you got ZL. Now, conclusion is that at load here D is equal to 0 distance, impedance is ZL. Then when you go towards the generator means source, towards the generator for lambda by 2 distance, again you got same impedance ZL. That means conclusion is on the lossless transmission line for lambda by 2 length, for each lambda by 2 length, impedance is repeated. What is impedance? Voltage by current. That means voltage and current repeats, then impedance also repeats. Then reflection coefficient is ratio of voltages. Reflection coefficient also repeats. The conclusion is on the transmission line for each lambda by 2 length, all the parameters like impedance, voltage, current, reflection coefficient, all the parameters repeat their values. That is why if you analyze the transmission line for lambda by 2 length, analyzing means what is gamma, what is impedance, what is voltage, etc. If you find, then no need to analyze for remaining length of the transmission line. That is why Smith chart is drawn for lambda by 2 length only. So lambda by 2 long transmission line behaves like impedance repeater, otherwise all parameters are going to repeat actually. So that is why Smith chart is drawn for lambda by 2 length, dear students. So I will write that here, that point. At load, impedance is ZL, and after lambda by 2 distance from load, transmission line impedance is ZL. So for each lambda by 2 distance on transmission line, all parameters like impedance, voltage, current, gamma, reflection coefficient, etc. values repeat. So analyzing transmission line for lambda by 2 length is sufficient. The Smith chart is drawn for lambda by 2 length. Okay. Now, lambda by 2 length long transmission line behaves like a impedance repeater that already we have written here. Okay. Now, if it is a lambda by 2 length, dear students, then ZL is equal to 0. That means short circuit. Okay. Then can you tell me what is the input impedance of this? Input impedance of lambda by 2 line is nothing but ZL, that is again 0. That means you take any transmission line whose length is lambda by 2, then automatically the input impedance becomes 0. Now this principle can be used to reject some frequencies, band reject filter. Example I will tell you. Example. So, for lambda by 2 transmission line, if load is short circuit, then input impedance is also short circuit. Okay. Now, so it can be used as band reject filter. It can be used as band reject filter. How I will tell you. Example. Coaxial cable having inner and outer conductors are used to transfer energy from source to load. Coaxial cable having inner and outer conductors are used to, or otherwise coaxial cable I said is used to, singular, is used to transfer energy from source to load at different frequencies like F1, F2, F3 dash. This many sufficient, F1, F2, F3. Okay, you can send any number of frequencies like this. If we want to stop F2 frequency, then near the load of coaxial cable, connect a short circuited lambda 2 by 2 Can you tell me, student, what is lambda 2 here? That is nothing but lambda is equal to V by F. So velocity divided by f, that means frequency 2 I have to take. So 2 times of frequency 2. So 1 by 2, lambda 2 is nothing but lambda is nothing but v by f. So lambda 2 means at f2 frequency we are calculating. So that means whenever f2 frequency comes, the length of the transmission line becomes lambda by 2. That means lambda 2 by 2, that is. So connect a short circuited lambda 2 by 2, that means v by 2 f2. Then it rejects f2 frequency. For example, you connect lambda 3 by 2 so that v by 2 f3, then it rejects f3 frequency. I will show you now. After showing the diagram, you will understand. So connect a short circuited lambda 2 by 2 long transmission line. Then this much is enough, because already we have written here. If we want to stop f2 frequency, then near the load of coaxial cable connect a short circuited lambda by 2 long transmission line as shown. So for example, here students, this is the, what is this, coaxial cable inner conductor, and this one is a coaxial cable outer conductor. This coaxial cable, now students, sometimes they take only single sheet here. This is of radius A, inner one, and this is of radius B. So this is radius A, and this one, this is of radius B. Sometimes they use a thickness also for that. So some thickness is there for that, like this. Okay. So I am putting here, this is conductor, I am writing it sigma. This is also conductor, this is also conductor. Here sigma region is actually dotted so that you will understand, and the between the conductors, that region is there here, dear students. This one, that is a dielectric medium. Now here there is a source. Here there is a source between the input side. Here source is there connected, and Vs source is there. This Vs source has a source has F1, F2, F3 commas. You have to put, student, F1 comma F2 comma F3 frequencies. Okay. You can send F1 frequency if you want. You tuning, na, you tune to F1 input source, then F1 goes. You tune to F2, then F2 goes. You tune to F3, then F3 frequency is transmitted. Here what is there actually? Here load is there, like this. Load is there. Okay, load ZL is there here at the output end. ZL is there. Now, or I can, otherwise I can connect like this also, so that you will be convenient. This one, there is no connection here. This is load, like this it is connected, because this ZL is connected from inner conductor to, here there is no connection here, and to the outer conductor. Now at the load, which frequencies come? F1 frequency is their input, F1 comes, F2 is their input, then F2 comes output also. If F3 frequency is there at input side, then at load F3 comes actually. Okay. But now if you want to stop the F2 frequency reaching the load, then what you do, near the load, here anywhere, like this, here there is no connection to this one, like this I am putting. The length of this transmission line is lambda 2 by 2 of wavelength the transmission line. So if you want, I will put this little thick conductor like this. This is transmission line of length lambda by 2 actually. Now anywhere you may think, sir, here more length is there. If you want to maintain same length, you can maintain same length, no problem. So like this. Okay, this length same, lambda 2 by 2. Now you know that the input impedance of this lambda by 2 is load impedance. Now I am short circuiting this load actually. So load is ZL is short circuited. Now this behaves like lambda by 2 transmission line for F2 frequency only. For F2 frequency only, it behaves like a lambda by 2 line. Whenever F2 frequency is sent here, then this transmission line, this lambda by 2 line behaves like a behaves like a lambda by 2 line. Then here load is short circuited. The input impedance is also short circuited. Now that signal has two paths. It can go like this also. It can go like this also. But that signal passes through this short circuit because whenever two paths are available, parallel paths, one is having low impedance, then signal prefers in passing through the low impedance path. So F2 frequency cannot reach here, because whenever frequency is F2 input frequency, then this transmission line behaves like a half wavelength line. For half wavelength line, it is a short circuit here, then input impedance is also short circuit. Then that signal F2 frequency signal passes through this transmission line and again it is reverted back. फिर वापस भेज देंगे, फिर इधर पहुंचेंगे नहीं है. So here only F1, F3 frequencies can reach load, and F2 frequency does not reach load because for F2 frequency, lambda by 2 transmission line offers short circuit at input end. So if it's offers short circuit end, then nothing will reach the load. Okay, right, dear students. Now I told you on the transmission line, for each lambda by 2 length, all values repeat. That is why Smith chart is drawn for lambda by 2 length. Okay. On transmission line, all values repeat for lambda by 2 length. So the distance between V maximum and V maximum is lambda by 2, comma, distance between V minimum and V minimum, that means they are called as two successive V minimum. This is called as two successive V maximum. Successive means first V maximum, then immediately next V maximum. That is called successive. Distance between V minimum and V minimum is lambda by 2. Okay. So as shown, I will show here. For example, it is like this, dear students. Total voltage waveform is like this. Then if total voltage waveform is like this, okay, this is a maximum voltage here. This is V maximum, and this is also V maximum. If this is the total voltage waveform with respect to distance here on the transmission line, so like this it is. Okay. Anyway, shall I write here? Doesn't matter. Okay. Now our focus is here, not this one. Actually, I am telling you this is total voltage waveform if distance changes on the transmission line. Now this one V maximum and V maximum coming, and here you have V minimum and V minimum like this. You have V minimum and V minimum. This is V minimum. This is V minimum. Okay. This is a voltage minimum. This is also voltage minimum. Now, what is the discussion here? The distance from here to here is lambda by 2. This one, lambda by 2. Similarly, here also distance from here to here is lambda by 2, like this. Now, between V maximum and V maximum, V minimum comes. Or otherwise, between V minimum and V minimum, V maximum comes. So then what is the distance between V maximum and V minimum? Half of lambda by 2, that is actually lambda by 4 distance. So this is actually V maximum and this is V minimum. This distance is lambda by 4, like this. Okay. So students, simply I am writing here, anywhere if you find V maximum, for example here you find V maximum, then again you will find V maximum after lambda by 2 distance. Next, for example, anywhere if you find here V minimum, then again after what do you say, lambda by 2 distance V minimum you will find. Okay. Now distance between V maximum and V minimum, this is V minimum and this is V maximum, is lambda by 4. Okay. Same thing applicable for I maximum to I maximum. No need to discuss that. Same thing happens for I maximum to I maximum distance is lambda by 2. I minimum to I minimum distance is lambda by 2. I minimum to I maximum is distance is lambda by 4. Next point, we are going to write one more note based on the normalized impedance. So this note is based on normalized impedance. Okay. Normalized impedance of the transmission line at any location divided by characteristic impedance. Actually, I am explaining you what is the meaning of normalization, dear students. For example, in many subjects you read the concepts, normalized concepts. Voltage by some other voltage. That ratio is called as normalized voltage. Power divided by some other power, that is called normalized power. So current by some other current, so that is called normalized current. Similarly, impedance divided by some other impedance is called normalized impedance. Here in the transmission lines, Z0 is characteristic impedance. So on the transmission line, you take any impedance and divide that impedance with characteristic impedance, that is called as normalized impedance. What is the use of that? You will see here that normalized impedance does not have units, and also that is linked with SWR here. We will see that standing wave ratio. Okay, normalized impedance. Normalized impedance is defined as the ratio of any impedance and characteristic, any impedance and characteristic impedance. Okay. Example I will tell you, ZL is load impedance What is this? It is load impedance. Of course, Z0 is characteristic impedance. Characteristic impedance. Then normalized load impedance. Simple, student. Small z is used for normalized impedance. So then you put suffix L. Small z means normalized impedance. Suffix L means normalized load impedance. Is small z is equal to load impedance divided by characteristic impedance. It is unit less. No units are there. So in this way, you can write here symbol is small z. No need to write, but if you want clarity, you can write small z only. That we were using a small z for distance, no? Distance from load source end. That same only, same one, same symbol. Actually, capital Z is symbol of impedance. Then small z is used for normalized impedance. Okay, capital R means resistance. Small r is used for normalized resistance. Capital X means reactance. Small x means normalized reactance. Okay. So, this is also important. That is why I kept in the box. In the examination, some exams they give normalized impedance is 3 and Z0 is 50. Then find load impedance. Then you must know what is normalized impedance meaning. You must know. Then only you can solve this question. Normalized load impedance is equal to load impedance divided by Z0. So this is 3 given. This is 50 given. So answer is 150. So in that way, the question is asked in exam. That is why I am telling you. Okay. Now we are going to write two statements in this note. Case 1. Case 1. On the transmission line at the location of voltage maximum, at the location of voltage maximum, that means V max, at the location of voltage maximum, current is minimum and impedance is maximum, because that meaning is that impedance maximum is equal to impedance is equal to voltage by current. Then numerator quantity maximum, denominator quantity minimum, then automatically impedance will be maximum. Actually, impedance is equal to V by I. So impedance is equal to V by I. So your common sense says numerator quantity maximum, denominator quantity minimum, then automatically this quantity is maximum. That is the statement written here. Okay. So on the transmission line, let us say you are going on the transmission line. So you are going on the transmission line like this. You found here voltage maximum. Then definitely at that location, transmission line current is the minimum. Then impedance is also maximum at that location. That is the statement. And transmission line at the location of voltage maximum, current is minimum, and impedance is maximum. So this is standard statement, student. Maximum. In this case, In this case, at the location of V maximum, impedance maximum is there, no? So impedance maximum divided by Z naught is called as normalized maximum impedance. So at the location of V maximum, we have normalized maximum impedance, small z maximum symbol, which is equal to standing wave ratio. So normalized maximum impedance is equal to standing wave ratio. Already we know that standing wave ratio 1 plus mod gamma divided by 1 minus mod gamma. These are all important points. So in this case, at the location of V maximum, impedance is maximum. Then if you divide that with Z naught, then we have normalized maximum impedance. Symbol is small z maximum. So that is which is equal to the SWR. If you want small z maximum, na, I can write there small z maximum is equal to maximum impedance by Z naught. That is equal to SWR. We will show that there. That is the formula. So here normalized maximum impedance is equal to small z maximum, that is equal to maximum impedance by Z naught. And this is the definition of this one. I told you that becomes this one is the definition of this one, and that becomes standing wave ratio. So I am writing here small z maximum is equal to, what is the definition? Definition is maximum impedance by Z naught is defined. It is definition, student. Maximum impedance divided by characteristic impedance is defined as normalized maximum impedance. Now, what is capital Z maximum in terms of voltage and current? Then that is V maximum divided by I minimum divided by Z naught. Okay. Now this is equal to V maximum divided by I minimum into Z naught. So dear students, this is equal to V maximum divided by current into impedance gives voltage, minimum current into impedance gives minimum voltage. So that is V minimum. Now standing wave ratio is defined as the ratio of voltage maximum and voltage minimum. So that is nothing but SWR. That is what the statement. Normalized maximum impedance symbol is small z maximum, and in terms of impedances, that is defined as maximum impedance divided by Z naught, and that is equal to, in terms of SWR, that becomes SWR. And this no need to study, just put that in the bracket, but that means no need to study that one. The statement is in the box. Okay. Similarly, case 2 is on the transmission line at the location of voltage minimum impedance is minimum, that is capital Z minimum, comma, current is maximum, I maximum, so that at voltage minimum location normalized minimum impedance is present and which is equal to 1 by SWR, 1 by standing wave ratio, which is equal to 1 by SWR. So that means I am writing here small z minimum is defined as impedance minimum divided by Z naught, that is equal to 1 by SWR. So here this Z minimum is nothing but where Z minimum is normalized minimum impedance. Okay, that Z minimum is equal to capital Z minimum by Z naught. Okay, that is the definition of that one. I wrote there, once again I am writing. So it is like this, student. Here you see, first of all, what is Z minimum? Actually, you students know that impedance is equal to voltage by current, dear students. Right? If numerator quantity is minimum, then denominator quantity is maximum. This will be the minimum then. That is the definition of minimum impedance. Minimum impedance is equal to voltage minimum divided by current maximum. That is the definition. So that is why at the location of voltage minimum, current maximum is there and impedance minimum is present. So anyway, now let us write that small z minimum is equal to, definition is normalized minimum impedance is equal to minimum impedance divided by Z naught. The definition of this in terms of voltage and current is voltage minimum divided by current maximum divided by Z naught. Now that is equal to V minimum divided by I maximum into Z naught. So that is equal to V minimum, maximum current multiplied with Z naught is maximum impedance, that is 1 divided by maximum voltage by minimum voltage, is defined as a standing wave ratio. So this is 1 by SWR. That is what we have written there. So you have to remember these statements many times in examination, in GATE exam also we got them, students. So they are important actually. We will solve the questions now, then you will understand the importance of those things. After completing this, we will do one small derivation, then we will put that in the box. Now the discussion is related to the distance from load end. Distance from load end at which first time voltage minimum occurs. For that one formula is there, we will do the derivation, and after that you are going to remember that formula. You see this. That is why, students, no need to learn any derivation. If you are preparing for examination, that means you have to remember the formulas. You must know how to use those formulas. Then you will be in top 10. You are doing unnecessary derivations, na? Maybe for engineering service examination you are preparing. For that you need derivations. Those derivations are little bit simple derivations only. They are not complicated derivations. For example, you see derivations in the waveguides, na? You keep doing derivations in waveguides and antennas, na? You can do derivations for continuously every day, 10 hours you do derivation in antennas, then those derivations will not complete for 1 month also. But after doing those many derivations, if I ask you a question, have you learned anything? You will not learn anything. You will practice maths. That is not called exam preparation. Exam preparation means you should be smart enough. You have to you have to focus on the formula which is required for examination. Then you have to understand that. Try to understand that. Then solve questions using that formula. That is required to crack the exam actually. Okay. Anyway, because whenever I was doing MTech in IIT Kanpur, there some people were doing MTech in antennas. So actually in 2 semesters, they read only antenna topics. They used to say, but even after doing derivations for 1 year, they were not completing because those many antennas are there. Those derivations are very complicated actually, complicated mathematics. वो मैथ्स भी डरता है वो डेरिवेशन देख के, इतना टफ रहता है वो डेरिवेशंस. कोई बात नहीं है. सो अभी छोटा डेरिवेशन कर रहा हूँ, अभी वो पढ़ने की जरूरत नहीं है, वो उसका फार्मूला देखना है, क्योंकि वो डेरिवेशन करने तक वो फार्मूला थोड़ा सा याद हो जाएगा आपको. नाउ लिसन स्टूडेंट्स, हियर आई एम राइटिंग the distance from load end, the distance from load end, that is called D minimum, at which the distance from load end, I will show the diagram also, the distance from load end, that means that is D minimum, I am calling the distance, at which first V minimum occurs is D minimum is equal to lambda by 4 pi plus theta gamma L. So this is the formula. Okay, dear friends, where gamma L is equal to ZL minus Z0 divided by ZL plus Z0. So this is complex in general. So that is mod gamma L e power j theta gamma L, students. Okay. Now where means where is gamma L? There is no gamma L, but I was talking of this one. Theta gamma L is the angle of reflection coefficient at load. Okay. So you remember this one, dear students. This one. This is the formula actually, D minimum formula. So you see this one. So where how you get theta gamma L? They give ZL and Z0. You find this gamma L, then that will have a magnitude and angle. So the angle of gamma L is kept here. D minimum formula, this one. Okay. If you want, I will solve this one. You keep watching now. Like this. One transmission line is there. The impedance is ZL. Total length of the transmission line is L. Now this is D is equal to 0. At a D distance, reflection coefficient is gamma D. At a D distance from load end, reflection coefficient is gamma D. And Z0 is characteristic impedance of the transmission line. I told you this characteristic impedance can be written here, anywhere. Sometimes they write like this also. And like analog circuits, don't think that if I put arrow mark, that means impedance is equal to Z0 here. Don't think like that. Don't confuse. This Z0 can be written anywhere, here, between the conductors, anywhere it is written. I told you Z0 is equal to root of R plus j omega L divided by G plus j omega C, there G and C conductance and capacitance are defined for the medium present between the conductors. That is why that can be written anywhere here. That can be written anywhere here. That is the reason. Okay. So now the reflection coefficient at d distance from load end is gamma d. That already you know. Formula also you know. Can you tell me what is the formula? Gamma d is equal to, I told you to remember that na, mod gamma L e power 2 alpha d. That was yeah. So e power, that is there. So that was minus 2 alpha d and e power j theta gamma L minus of 2 beta d. So this was the reflection coefficient at d distance. So mod gamma L e power minus 2 alpha d e power j theta gamma L minus 2 beta d. Now this one is called modulus of gamma d is equal to mod gamma L, that means magnitude e power minus 2 alpha d. What is modulus of e power j theta? Root of cos square theta plus sin square theta, that is 1. So that is magnitude. Then what is the angle of gamma d, dear students? Angle of gamma d is equal to that is theta gamma L minus 2 beta d. Now at the location of V minimum, how you get voltage minimum, dear friends? How you get voltage minimum? Incident voltage and reflected voltage have opposite sign. So at the location of V minimum, incident voltage and reflected voltage have opposite sign. Opposite sign. That is why, for example, V incident and V reflected have opposite sign. Na? Then total voltage is sum of incident and reflected. Then if they subtract and you get V minimum. Total voltage minimum you get. So at the location of total voltage minimum, incident voltage and reflected voltage have opposite sign. So reflection coefficient angle is plus or minus pi. That means the voltage difference can be phase difference can be plus minus pi, and then only I told you e power j plus minus pi is equal to cos pi plus minus j sin pi, dear student. This is 0, this is minus 1. So that is why V incident and V reflected, they are subtracted and you get total voltage minimum. So reflection coefficient angle is plus minus pi. Okay. Among them, minimum angle is again minus pi, maximum angle is plus pi. So if you want least distance, you have to substitute minus pi. Now here reflection coefficient is nothing but if you have any doubt, then reflection coefficient is nothing but reflected voltage divided by incident voltage. I told you if they have this one and this one have opposite sign, no? Then opposite sign means the phase of this one differ by 180 degrees. That is the meaning of that. Okay, because reflection coefficient is defined as reflected voltage by incident voltage. If they have a opposite sign, then phase difference is plus or minus 180. Anyway, that means On the transmission line, here this is ZL, and let us say this is D is equal to 0. I can write distances the bottom side or otherwise top side, doesn't matter. ओके, ऊपर भी लिख सकता है डिस्टेंस, इधर नीचे भी लिख सकता है, कोई टेंशन नहीं है। मान लीजिए व्हेन यू कम टू डी मिनिमम डिस्टेंस, कुछ डी मिनिमम 2 मीटर आया इधर से, आप लोड से 2 मीटर आया मान लीजिए, लोड से 2 मीटर आने के बाद आप लोग पहली बार वोल्टेज मिनिमम को देखा है। अभी तक वोल्टेज मिनिमम देखा ही नहीं है आप लोग, पहली बार देख लिया आप लोग 2 मीटर डिस्टेंस में। वो 2 मीटर डिस्टेंस को हम डी मिनिमम करके नाम दे दिया। वो डी मिनिमम के लिए फॉर्मूला चाहिए, वो फॉर्मूला यही है। सो डियर स्टूडेंट्स, here d0, for example, you are coming like this. When you came here, you came on the transmission line for 2 meter distance. First time you found v minimum, then you are calling that distance as a d minimum. What is the formula of that one? Now let us derive that here at this location. First time voltage minimum you found, so this is first v minimum. Okay. Now at the location of, that means here d0, this distance is a d minimum. At the location of d minimum, you will have gamma d reflection coefficient at the d minimum location. Now already you know angle of reflection coefficient at d distance is theta gamma L minus 2 beta d. Reflection coefficient angle at d is equal to d minimum distance, then theta gamma L minus of 2 beta d minimum. Now what is the angle of reflection coefficient at d minimum? That means at voltage minimum, I wrote here at the location of voltage minimum, incident and reflected voltage have opposite sign, so reflection coefficient angle is plus or minus pi. I told you we want least distance, so you take negative angle minus pi. Then what happens if you take plus pi? Then the next voltage minimum you get actually. So that is minus pi you are taking, then theta gamma L, because at the location of d minimum you have first time voltage minimum, so that is 2 times 2 pi by lambda into d minimum. Now from this you send this side, no, you send this side, then you get theta gamma L plus pi, you send this one that side. So from this 4 pi by lambda, so 4 pi by lambda multiplied with d minimum is equal to pi plus theta gamma L. Okay, so d minimum is equal to lambda divided by 4 pi plus theta gamma L. Okay, dear friends, so this is what you got, the formula, that one. Now basically dear students, now what happens if you go lambda by 4 distance from v minimum this side, lambda by 4 distance, now you will have a v maximum, So here I am writing here dear students, so here I will write that in the note, otherwise I will put in the box, the distance from load end at which first voltage maximum occurs. So the distance from load end, I am calling that as a d maximum. The distance from load end, that means I am calling that as a d maximum, at which first v maximum occurs, is d maximum is equal to, now students, I told you already, I wrote in the note, wherever voltage minimum is there, you come this side, for example, lambda by 4 distance, this side, then automatically you will have a V maximum. So that means D minimum this side means minus lambda by 4. So D maximum is equal to D minimum and minus lambda by 4. And this side also, for example, if this side it is not there, actually if voltage minimum is there here, this side lambda by 4 distance you will find voltage maximum, there is no doubt. But the transmission line length overall here is less than lambda by 4, then definitely you will not find V maximum here. Then this side you will have a V maximum at lambda by 4 distance. So you will find V maximum at lambda by 4 distance from here again. So this side, if total length of the transmission line is less than lambda by 4, then you can't find V maximum this side. Then you will find V maximum this side at lambda by 4 distance. So that means D minimum plus lambda by 4, that is, so this is plus lambda by 4. So the distance from load end at which first time voltage maximum occurs is equal to D maximum is equal to D minimum plus or minus lambda by 4. So already what do you say, D minimum formula you know, you find that D minimum, then plus or minus lambda by 4 you take, you get the first voltage maximum location you will get. Okay. So this is the formula for that one. This is the derivation, you don't bother about this derivation. You remember this formula, and here theta gamma L is calculated from reflection coefficient at load. Then you take plus or minus lambda, and which one to take here, student? Which one to take? For example, first question was there. In that question, D maximum is equal to, let us say D minimum is 3, then plus or minus lambda by 4 you got 1, student. लैम्डा देने के बाद लैम्डा by 4 1 आया, so then 3 plus 1 and automatically 3 minus 1, two options, so 2 and 4, this is positive value and least, so first time voltage maximum occurs at 2 meters from load. For example, there is second question, in that I found that D minimum was 6 and lambda by 4 calculated 10, then 6 minus 10 minus 4 you get, then 6 plus 10 16 you get, so but minus 4 means there is no transmission line there, that is the meaning, because transmission line at load D is equal to 0 distance, there is no negative distance, but that means this doesn't exist. So from load 16 meters D maximum exist, like that, that is the meaning actually. These two examples I have taken, don't ask me, sir, how do you know it is 3, how do you know it is 1? I am assuming that after calculating D minimum I got 3 in one question, then lambda by 4 I got 1, then which is the distance at which first time voltage maximum occurs, 2 meters. Then in second question I found D minimum I calculated, I got 6, then lambda by 4 value is 10, then 6 plus 10 is 16, 6 minus 10 is minus 4, then transmission line cannot have negative length, because transmission line length at load is D0, then you will have a positive length, so this doesn't exist. So first time voltage maximum occurs at 16 meters from load, so that is the way you take here, dear students, right? So dear students, let us solve some questions. After solving some questions, again we will continue the theory. Now this is a transmission line chapter, first question. So workbook na, workbook, so transmission lines. So here first question, calculate the input impedance of a lossless transmission line of the following lengths and load impedance is ZL. So first one is length is lambda by 8 given. Already we have solved, na dear friends. So it is lossless transmission line. Now what is the input impedance of lambda by 8 transmission line, student? Already we have solved in the notes in cases. So Z0 ZL plus JZ0 divided by Z0 plus JZL. Okay, so this is the formula. Next, in the second part, total length is given as lambda by 4. For this also we have calculated Zin of lambda by 4 is equal to Z0 square by ZL. Already we found this one. Next, third one, it is asked the total length is equal to lambda by 2, it is asked. So what is the input impedance of lambda by 2, dear students? Load impedance. Now fourth part is it is asked length of the transmission line is given as lambda. You have to find input impedance for this. So you know, students, this is lambda is nothing but you can write this lambda as 2 times lambda by 2. So it is integer multiple of lambda by 2. For each lambda by 2, load impedance is repeated and it is 2 times of that. So ultimately, once again, Zin of lambda is nothing but ZL only, because it is lambda is 2 times of lambda by 2. For each lambda by 2, impedance repeats. Load impedance is ZL, and after lambda by 2, it is again ZL. Again after one more lambda by 2, impedance is ZL only, transmission line impedance. So that is ZL, right? Okay. Now, second question, the Zin, that means input impedance, is of how much, or otherwise is of which nature he is saying. Nature means for example, students, impedance is equal to J positive, that is inductive. J negative you get, that is capacitive. For example, you got some 20 like that, that is resistive. Example, positive real you got. So 20 like that, resistive nature, input impedance. 0 you got, 0, J0 minus J0. So J into 0 or otherwise minus J0, 0 you got, then that is short circuit nature. Then you got infinity, J infinity minus J infinity, they are all open circuit nature. Open circuit. And this one is actually what? Positive and real you got. Positive real. That means resistive nature. So which nature is that? The input impedance is of dash nature, maybe inductive nature, capacitive nature, like that, open circuit nature. We have to answer that one by finding the input impedance. Okay. So the input is of dash nature for a lossless line, of lambda by 8 length, and Z0 is equal to 50 ohm and has a 50 ohm inductive load. That means it is given Z0 is equal to 50 ohm, ZL is equal to inductive 50 ohm means J50. That is the meaning. Now, what is the nature of lossless lambda by 8 transmission line? You know that Zin of lambda by 8 is equal to Z0 plus ZL plus JZ0 divided by Z0 plus JZL. Now, Z0 is actually 50 and ZL is J50. J into Z0 is JZ0, Z0 is 50. So Z0 is 50 plus ZL is J50. So ultimately you get 50 into J100 divided by 50 minus J into J square, 50 minus 50. So ultimately denominator you got 0. So 1 by 0 is infinity. So ultimately you got J infinity. Anyway, so it is open circuit nature. Which nature? Input is input of lambda by 8 transmission line is open circuit nature. That is the meaning. Open circuit in nature. Okay. Repeat the above problem for repeat the above problem for a lambda by 4 line. Now Zin of lambda by 4 is equal to Z0 square by ZL. That means Z0 square means 50 square. ZL is J50. That is nothing but minus J50, dear students. Minus J. So you get this one. This is which nature, dear students? This is capacitive in nature. So capacitive in nature. Option is B for that. For this option is D. Anyway, question number 4. Repeat the above problem for lambda by 2 line. So repeat the above problem for a lambda by 2 line. That means Zin of lambda by 2 is equal to ZL only. ZL is J50. So answer is inductive nature. Inductive nature, because impedance is imaginary and positive, that is inductive nature. J omega L, that one. This is minus J by omega C, like that. Question number 5. So diagram, everything is given. Here one transmission line is there of length lambda by 4. Bottom side is given length here. Lambda by 4 is given like this. Now characteristic impedance of Z0, characteristic impedance of second line, here one more line is there, that is 200 ohm is given. Now this is line 2. That is why Z0 means characteristic impedance, 2 means for second line. The length of this line is lambda by 4. And one more line is there here. That line is once again line 1. The length is lambda by 4 once again. So the length of this is lambda by 4. Okay. Now this is 150 ohm. And this is first line. Characteristic impedance of first line is equal to 100 ohm. This is line 1. Now what is the input impedance of this one? So that is the question. Actually it is written here Zin. So what is the input impedance of this one? Now how you solve this one, dear students? For first line, the input impedance is, this is line 1, Zin of first line is equal to, this is lambda by 4 line. For lambda by 4 line, input impedance is equal to characteristic impedance whole square, that is Z01 whole square divided by ZL of this. So Z01 whole square means 100 square divided by 150. So 100 square divided by 150 it is. So here Z01 is equal to, so this is 100 into 100 divided by 150, that is 1000 divided by 15 you get. So here the input impedance of the line 1 behaves like a load impedance to the line 2. Reason is, it is like analog circuits. If I assume this is transistor 1, assume this is transistor 2, the output of the transistor 1 is given to the input of the transistor 2. So input impedance of the transistor 2, second transistor, behaves like a load impedance to the first transistor, like that it is. So here I am writing the input impedance of line 1, that is Zin1, behaves like a load impedance to the line 2. Okay. So now for this transmission line ZL, I have taken this as a ZL and I will take this as a ZL dash. This ZL dash is equal to the Zn. Okay. So that means the ZL dash is equal to the Zin of first line. So I called this impedance as ZL. The load impedance of the this line, lambda by 4 line, I am calling it as ZL dash. Now dear students, here the input impedance of this one, this is once again lambda by 4 line only. So the input impedance of lambda by 4 line is equal to characteristic impedance of this one whole square divided by, what do you say, load impedance of this one, that is ZL dash. So ultimately Zin of lambda by 4 is equal to Z02 whole square is Z02 square divided by ZL dash, that is nothing but 200 square divided by ZL dash is nothing but Zin1. Here I have written, that is 1000 divided by 15. So ultimately here 3 zeros cancel, 1 zero remains. So this is the answer. Print miss. No students, here no 4 is there. 2 into 2 4. This is 4 and 1 zero remains. 60 this is. 600 ohm. Option A. The answer B it is. Right? Next question. Question number 6. There is a lambda by 8 length here. Okay. Now you need Zin of this. And here lambda by 2 is there. That is 2 R naught characteristic impedance. This is R naught by 2. This is lambda by 4. And this is lambda by 2. Like this it is given. All transmission line sections in figure have a characteristic impedance R0 plus J0. That means the characteristic impedance is this R0, the characteristic impedance of this R0, this is R0, it is given. It is given in the question. The input impedance Zin equal to the, here it is shown here, the input impedance you have to find. That is the question. Now this is also simple question. Can you tell me what is the input impedance of lambda by 2 section? this input impedance of lambda by 2 line. Now the input impedance of lambda by 2 line is equal to load impedance of this one, ZL of this one. So I can call this as a ZL1 and this as a ZL2 and this as a ZL3. I will write the load impedance of this one is what do you say, or otherwise I will put like this. There is no load impedance here. For this one, the load impedance is ZL3 for this load impedance. The load impedance of this one is equal to the input impedance of these two transmission lines. So why I will tell you anyway. First let us find this one. The input impedance of this lambda by 2 line is equal to load impedance of this one, that is ZL1, that is 2R0. Now what is the input impedance of this is lambda by 4. So lambda by 4 is equal to this characteristic impedance whole square divided by load impedance actually. So that is ZL2, that is nothing but R0 square divided by R0 divided by 2. So ultimately you get 2R0. Now if you see carefully, for example here if I current is going, that I current is divided like I1 and I2 it is divided. Now this current goes here and again comes back here I1 current and in this I2 current goes like this and again that I2 current goes like this. Ultimately here I current comes. That means like network theory, these two are in parallel because the current is divided. So this is input impedance 2 or not, this is input impedance 2 or not, these two are in parallel. So overall input impedance becomes a parallel combination of 2 or not and 2 or not. So the input impedance of these two sections Z in, I will remove this for time being. So the input impedance of these two sections is nothing but I will write here Z in is nothing but 2 R naught parallel combination of 2 R naught, that is 2 R naught into parallel combination means 2 R naught into 2 R naught divided by 2 R naught plus 2 R naught. Anyway that you know. So this is 4 R naught square divided by 4 R naught, that becomes R naught. So here the input impedance is R naught. The input impedance of both the transmission lines is R0. Now you are supplying energy from this transmission line to the input impedance of these transmission lines. That is why the input impedance of this transmission line behaves like a load impedance to this transmission line. Now if I call this as a load impedance to this transmission line as a ZL3, this is third one, that is equal to ZL3 is a load impedance of this transmission line, that is not given actually. So I am calling this as a ZL3, so that ZL3 is equal to Zin of these two transmission lines. Now this is a lambda by 8 transmission line, this one lambda by 8 transmission line. For this transmission line, Zin of lambda by 8 is equal to Z0 of this transmission line, that is R0. Then ZL of this transmission line is ZL3 plus J Z0 divided by Z0 plus J ZL3. So that is nothing but Z0 is R0 here and ZL3 is also R0 actually, plus J R0 divided by R0 plus J R0. So ultimately you get R0. So that is the answer. R0 is the answer. Next question. A transmission line whose one end is short circuited has its characteristic impedance R naught on the other end. That means here two statements are given, student. There is a transmission line whose one end is short circuited and has its characteristic impedance R naught. That characteristic impedance R naught is given, and on the other end also this R naught is connected. So that is the meaning of that. We'll draw the diagram. Calculate the impedance at the center of the transmission line if its length is lambda by 4. Calculate the impedance at the center of transmission line if the length is lambda by 4. Now that means that question is like this, student. This is the transmission line. The characteristic impedance of this is R naught. It is given characteristic impedance R naught. One end is short circuited like this. So it is ZL is equal to 0. Other end is terminated with its characteristic impedance like this R naught. Then overall length of this is equal to lambda by 4 like this. Now what is the impedance of this transmission line at the center of the transmission line? That means center means here this is lambda by 8 distance, this is lambda by 8 distance. So you need the impedance here like input impedance Zin. Now what to do? It is like network theory. In network theory, that means electrical circuits and networks. In electrical circuits and networks, how to find Thevenin impedance and Norton impedance? For example, at these ends, these are open ends, at these ends you want impedance, that's what we need. Then what we do, we connect some voltage source at these ends, then this voltage source generates I current, then that I current is split as I1 and split as I2. सो हम लोगों को इस एंड पे ये ओपन एंड्स पे इम्पिडेंस चाहिए. हम लोग थेवेनिन एंड नॉर्टन सर्क्यूट्स में इम्पिडेंस फाइंड करने का प्रोसीजर है. सो जिस जगह में आपको इम्पिडेंस चाहिए, इस लोकेशन में इम्पिडेंस चाहिए, वो उसका बीच में वी वोल्टेज सोर्स कनेक्ट कर लेता है. टेस्टिंग वोल्टेज सोर्स है वो, उससे जरूर आई करंट जनरेट होता है. वो आई करंट है इस तरफ डिवाइड हो गया. अभी डिवाइड होके फिर इधर ऐसा जाके I1 करंट फिर वापस आ जाएगा. इसमें से I1 करंट इधर वापस आ जाएगा. फिर इसमें से I2 करंट जितना भी जाएगा वो वापस आ जाएगा. फिर ओवरऑल करंट I हो गया. सो करंट डिवाइड, सो करंट इज डिवाइडिंग. I1 करंट इज गोइंग लाइक दिस कमिंग बैक, I2 current is going like this coming back. Again overall current is I. That means this lambda by 8 section and lambda by 8 section, they are in parallel combination. So I can draw here equivalent circuit like this. So parallel combination means what now? Find input impedance of this one of lambda by 8 line. Find input impedance of this one of lambda by 8 line. Then parallel combination of them gives the input impedance. I am redrawing that diagram. Here it is like this, situation is like this. So there is one lambda by 8 line. So it one is this is short circuited of lambda by 8. Okay. Now one more transmission line is there here like this. Okay. This is connected with R naught. Now we want this impedance Zin is required. That is the meaning. So what is the input impedance of this one? This characteristic impedance is R naught. This is also R naught. Let us call this as a Z in 1. Let us call this as a Z in 2. And we want Z in. That Z in is nothing but Z in 1 parallel with Z in 2. So, here this is also lambda by 8 line. Okay. Now, Z in 1 is equal to, for this, na, that is equal to, directly I am writing R naught. Then here, first I will write formula so that you will be comfortable. What is the input impedance of lambda by 8 line? Z naught ZL plus JZ naught divided by Z naught plus JZL. Now, what is Z in 1? That is lambda by 8 line. This is impedance of lambda by 8 line. For this, Z naught is what? R naught. Then for this, ZL is what? R naught. Plus for this, Z naught is R naught divided by R naught plus J R naught. Cancel, you get R naught. Then what is Z in 2? That is also lambda by 8 line. For this, Z naught is R naught. Then ZL is here 0. So 0 plus J R naught divided by Z naught is R naught. So ultimately you get ZL plus JZ naught. Here print means is there, students. This is ZL, na? Right? ZL this is. Okay. Z naught ZL plus JZ naught divided by Z naught plus JZL. Here ZL is what, student, for this short circuited 0. So ultimately this is R naught, R naught, R naught cancel. You get J R naught. So the input impedance of this section is R naught. The input impedance of this section is J R naught. Now this Z in is equal to Z in 1 parallel combination with Z in 2. That is this multiplied with this R naught into J R naught divided by sum of them R naught plus J R naught. So here J R naught square by R naught plus J R naught. So R naught cancel. So ultimately answer is J R naught divided by 1 plus J1. So this is the answer, student. J R naught by 1 plus J1 is the answer. Right. Next, question number 8. A transmission line of 10 meter length. Students, I told you, no, transmission line length is always measured in terms of lambdas. But here it is given in meters, 10 meters. That means you have to convert the transmission line length into the wavelengths. Definitely for that frequency should be given. So in this question frequency is given. So 10 meter length operates at 10 megahertz frequency here, 10 megahertz. Okay. Assume the line to be lossless. Assume the transmission line to be lossless, having a velocity of 2 into 10 to the power 8 meter per second for the wave. Okay. Calculate the input impedance of the line terminated with a load impedance. So calculate the input impedance of the line is terminated with a load of 30 minus J40 ohm, and given its characteristic impedance is 50 ohm. Now actually one by one I will read and I will write. So what is the length of the transmission line? 10 meter it is given. What is the frequency of operation? 10 megahertz. So it is a lossless transmission line. What is the velocity given on the transmission line? 2 into 10 power 8 meter per second is given. Now calculate the input impedance. That means you have to find Zin of the line terminated with a load impedance. ZL is equal to 30 minus J40. Then what is the characteristic impedance of that? 50 ohm. Now you have to find Zin. For that purpose, you should know what is the length of the transmission line. So I will find like this: lambda is equal to V by F. That V is given as 2 into 10 to the power 8 divided by frequency is 10 megahertz. So ultimately, this is 10 power 7. So 20 meters you get. Now, once if you calculate this one, let us take the ratio of length and lambda, because length also in meters, lambda also in meters, so that you get L and lambda relation. Length is given as 10 meter and lambda is 20. So ultimately lambda is equal to L is equal to cancel, so lambda by 2 you get. That means length of this transmission line is lambda by 2. So now the input impedance of this lambda by 2 transmission line is ZL. So that implies the input impedance of this lambda by 2 line is nothing but load impedance only, 30 minus J40. So that is the answer. So option is C. Option C. Okay. Now you have to repeat this question. You have to repeat this. He is saying, repeat the above problem if the frequency is 5 megahertz. Students, here frequency was 10 megahertz. If you put 5 megahertz here, then you get here 40 meter. Then 10 by 40, you get lambda by 4. Then for our lambda by 4 transmission line, impedance is Z0 square by ZL. So you get 30 plus J40. So here you see that question. Repeat the above problem if frequency F is equal to 5 megahertz. Okay. Then here lambda is equal to V by F. So V is 2 into 10 to the power 8. This is 5 into 10 to the power 6. Then here this is 200 divided by this one, 200 divided by 5, that is 40 meters. Now L by lambda, L is given as 10, lambda is 40, implies L is equal to lambda by 4. Now Zin of lambda by 4 is equal to Z0 square by ZL. Now in previous question, characteristic impedance is given as 50 square divided by ZL is 30 minus J40. So this is equal to 50 square 30 plus J40 divided by 30 plus J40. In already 30 minus J40 was there. So ultimately you get 30 plus J40 students after calculating this one. So option is A. Okay. Question number 10. A transmission line is short circuited at one end and has an electrical path length, path means distance, an electrical path length of pi by 4. That means what is the student? Beta L, na? I told you that is equal to beta L. Beta into distance is called electrical length of the transmission line. If its input impedance is J60 ohm, then its characteristic impedance is? Characteristic impedance is, that means you have to find Z0, dear students. A transmission line is short circuited at one end. Okay, this is transmission line. Now load is short circuited, has its electrical path length, that means that the transmission line length is L, and given beta L is equal to pi by 4, it is given, students. Okay, if its input impedance is that means Zin of this is J60 is given, J60 ohm. Then characteristic impedance is, let us take Z0 is the characteristic impedance, you have to find this one. So beta into L is given as what do you say, pi by 4. Now I will write this beta L. Beta L is equal to pi by 4 is given. So here, students, let us take D0, then D is equal to L, that means total length, you get input impedance. Already we know the formula. What is the input impedance when load is short circuited? Already you know that J Z0 tan beta L. Actually that was Z0 tan H gamma L, but this one is lossless, we have to take. So then J Z0 tan beta L you get. So this is the formula of input impedance. Now that person gave this Zin, he has given it as 60, J60, Zin is given as J60, and J Z0 we have to find tan beta L for this line is given as pi by 4. So J60 is equal to JZ0, this is 1 actually, that implies Z0 is equal to 60, characteristic impedance, 60 ohm is the answer. Now question number 11. In the above problem, if operational frequency was 12 megahertz, that means in this frequency was 12 megahertz he has given. What is the input impedance? What is Zin? If the frequency is shifted to 24 megahertz. Now let me write, my dear friends, let us take F1 is equal to 12 megahertz. Then he has given beta 1 into L, that is beta 1. Beta frequency, beta is equal to omega root LC, students, formula, into L. So beta 1 means omega 1, that means at frequency 1, beta 1 is there. And he has given this value in the previous question as a pi by 4. Once again, students, in previous question, beta into L, beta formula in transmission line is omega root LC, beta into L is given as lambda by, pi by 4 at frequency 12 megahertz. Now what I am doing, I am taking that frequency as 12 megahertz as F1 frequency, then omega 1, 2 pi F1, then beta 1 I am calling it as, because second frequency is given here. Now second frequency is given as 24 megahertz, that is nothing but 2 times of F1, 2 times of F1, 2 into 12 is 24. That means at this frequency, beta 2 L is equal to omega 2 root LC into L, that is nothing but W2 is nothing but 2W1. So 2W1 root LC into L. So that is nothing but 2 into W1 root LC into L is pi by 4. So ultimately you get this is pi by 2. That means in this question beta L was pi by 4. Now in this question beta L is pi by 2 it has become. So now what is the question? What is Zn if the frequency is shifted to 24? Now if frequency is shifted to 24, then beta 2L becomes what do you say, pi by 2. Now here the question is like this. Okay, Jz not tan beta L. Now the question is like this. ZL0 length frequency of operation for this question beta 2L is pi by 2 here. Now what is the input impedance here? JZ0 actually short circuit, no, same question, but frequency is doubled. JZ0 tan beta L, this time this is beta 2. So JZ0 tan beta 2 into L is pi by 2. So JZ0 into infinity, that is J infinity, students. Okay, tan pi by 2 is infinity. So answer is actually option B. Option B, infinity is there, so that is the answer. J infinity or infinity both are same. So question number 12. In the above question, what is the equivalent inductance at the input terminals at 12 MHz? That means this 12 MHz is a reference with question number 10, student. In the above question means that is question number 10, student. How do I know? Because in question number 10 only frequency was 12 MHz. So in the above question or otherwise above problem, what is the equivalent inductance? What is the equivalent inductance? What is the equivalent inductance at the input terminals? At 12 MHz. That means the input impedance given in the question number 10 at 12 MHz is J60. It is given, student. So it is given in question 10, in problem 10. Okay. So now frequency is given as 12 MHz. My dear students, J60 means it is inductive. So inductive impedance is for inductor impedance for inductor impedance is equal to Z of j omega. You say directly I will write j omega L. That means j omega L is equal to J60. Now j into 2 into pi into frequency is 12 into 10 to the power 6 into inductance is equal to J60. From this inductance is equal to J cancel. From this inductance is equal to 60 by 2 into pi into 12 into 10 to the power 6 Henry. This value you get 2.5 divided by pi micro Henry you get. So this is the answer. Option is A. Option A. Okay. So this is 12. You get 5 by 2 is 2.5. Then pi is there. 10 power minus 6. Okay.